Good morning, everyone, and welcome back to Math 098 Elementary Algebra. For today's class, we are finally ready to get into Unit 7, which is factoring. So this is a pretty big chapter. It's a very significant chapter, being that as long as you have a really strong understanding of factoring, you're going to be successful in your next class, okay? So this section especially is something that you want to continue to practice repeatedly. Good morning, Cindy. You want to practice this repeatedly so that you can be successful in your next algebra class, okay? All right, we are ready to get into factoring. Let's see how this goes. We're going to start off by learning about how to factor out the GCF, what it means, what it looks like, and kind of expanding on that idea. And I think that's all we'll end up covering today. I try to cover maybe 1 or 2 techniques a day, but nothing more than that. I don't want it to be too overwhelming. As always, good morning, Johanna. As always, put your questions in the chat so that I can help guide you through this. This is our last big unit. After this, we have Unit 8, and it's this big. It's super, 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 super small. All right, everyone? Let's check it out. Factoring out the GCF. Notice here that I've written step 1. If you have your guided notes handy, you actually will notice a flow chart on the very last page of your guided notes. So I just want to show you really quickly what that looks like. It looks like this. It's the very last page. It says steps to help you factor polynomials. The very first thing that it says here is there a GCF? Is it a leading negative? If it is yes, you'll do this step. If there is none, you'll move to this step. So I want you to think about this flow chart as we learn our factoring techniques. We're going to eventually learn how to factor binomials, trinomials, 4-term polynomials, etc. Okay? So I'm going to set this aside. I urge you all to do the same just so you can see the flow chart and notice what it is that we're learning. Okay. First things first, what is the GCF? Well, the GCF is the greatest common factor. I wanted to refresh your memory on the differences between multiples and factors. A multiple of a number is that number multiplied by an integer, right? Multiples. We actually saw multiples when we were looking for the lowest common denominator. We said, what is the lowest common multiple? That will help us find the LCD. So for instance, multiples of 20 are 20, 40, 60, 80, etc. If you look at factors, factors are found by breaking a number down into products that form the original number. Okay, so for instance, factors of 20 are 1 and 20 because 1 times 20 is 20. 2 times 10 is 20. 4 times 5 is 20. Okay, so notice here that we're essentially pairing these factors up and they result in a 20. Okay, so let's practice finding the GCF of a set of terms. What may be helpful to you is to write out the factor pairs. So we already have 20 here. That's taken care of. Let's write out the factor pairs for 45. And if you want, you could go ahead and grab your calculator because you may need it, and that's okay. I want you all to be very comfortable saying, you know, I'm good with my factors, but maybe I'm not perfect, and maybe I want to be able to kind of look things up and double check my work. Okay, be confident in that. For 45, our first pair of factors is 1 times 45. We know that our number here is odd. It doesn't end in a multiple of 2, so we know it's not divisible by 2. Notice that 4 plus 5 is 9, so that means it's actually divisible by 3. So 3 times 15 gives us 45. We also know that 5 can go into 45, so it's 5 times 9. And that actually encompasses all of the factors of 45. We're going to do the same thing with 90. So we have 1 times 90. It ends in a 0, so we know it's definitely divisible by 2. Think even numbers, right? 2 times 45. 9 plus 0 is 9, and 9 is a multiple of 3, so 3 goes into 90. 3 times 30. We can try 90 divided by 4. Nope, that doesn't work. But because the 90 ends in a 0, it's definitely divisible by 5. So 5 goes into 90 18 times. Let's check to see if 6 goes into 90, and it does. So 6 times 15 is 90, not 7, not 8, but 9 can go into 90, so 9 times 10. And we've covered all of our factor pairs for 90. So now that we have the factors of 20, the factors of 45, and the factors of 90, we simply have to find the greatest common factor. So as I look at each of these lists, I'm noticing that they all have a 5, right? Do they all have a 10? No. Do they all have a 20? No. So our greatest common factor in this case is going to be 5. So GCF is equal to 5. Good morning, Ethan. No worries. This is how you would essentially identify the greatest common factor for numerical bases. Let's talk about what happens when you find the GCF for a variable base. So notice here you have m to the 9th, m to the 3rd, m to the 7th. When I teach this section in class, I try to have everyone visualize what this looks like. So I would say something like, Doc, in front of you, you have 9 M&Ms, right? I know we're talking candy. Just pretend you have 9 M&Ms in front of you. Ethan, you're going to have 3 M&Ms in front of you. And then let's do Ryan, you're going to have 7 M&Ms in front of you. So if you can all visualize how many M&Ms every person or each of those 3 people have, then you can answer the question, which is, at most, how many M&Ms can you take from each of them so that they will all be the same, right? Meaning, how many M&Ms can you remove from each person so that each of those piles are identical, right? And you would have to say, well, 3. Think about this logically. If Doc had 9 M&Ms in front of him, right? But Ryan has 3, and actually, I don't even know who I said, and we'll do Ethan has 7, then Ryan with the 3 can only give 3, right? Even though Doc has 9 and Ethan has 7, Ryan can only give 3. So it only makes sense that you take 3 from each group so that they're all matching, right? So that that donation is all identical. That's what we mean by looking at the greatest common factor for variable bases. What you end up doing is you say, well, first off, do they all have the same thing, right? Are they all M&Ms? In this case, yes, they all have M&Ms. And then you say, well, okay, at most, how many can we take so that we're taking equal contributions? And you would say, okay, well, 3. That's all I can do. It's not like you can say to Ryan, I know you only got 3, but you better give me more. Like, what is he going to do? Like, manifest some more M&Ms? Ta-da! And if he could, then I'm coming over because I want some M&Ms. All right? But it's not possible. So what you end up noticing is that when you look at variable bases, your GCF is always going to be the lowest power because that's the most they can give, right? I hope that makes sense. As we look at a bunch of them, I think you're going to realize, oh yeah, okay, I can't take more because it doesn't have it. It's like asking Ryan, give me more than 3 M&Ms. I want that, you're like bullying Ryan. Ryan's like, no, I don't have it. Stop. Okay, let's take a look. So the GCF in this case, again, notice m to the 9th, m to the 3rd, m to the 7th. So our GCF is going to be the variable with the smallest power. So out of these 3 options, the GCF is m to the 3rd because that's the most you can take out of each of these terms. Okay? Another way to think about this is if I actually wrote it out. So m to the 9th is 9, 4, 5, 6, 7, 8, 9. M to the 3rd is 3 m's, 1, 2, 3. M to the 7th is 7 m's, 1, 2, 3, 4, 5, 6, 7. And then notice that they have 1, 2, 3 in common, right? The rest are excess. So your GCF is m to the 3rd. Hopefully that's even clearer looking at this expression in that way. Take a look at number 3. We have x to the 5th, y to the 3rd, z. Remember, if you see a variable base without a power, we know that it's actually a power of 1. So let's write that in there. X to the 10th, y to the 11th, z to the 9th. X to the 2nd, y to the 3rd, z to the 1st. So in finding the GCF yet again, we say, okay, does every term have an x as a variable base? And you would say, yes, they do. And then you say, well, we have an x to the 5th, x to the 10th, x to the 2nd. Out of these 3, at most, how many can we take? Well, at most, we can only take x to the 2nd, okay? You could take 5 x's out of here, and you could take 5 x's out of here, but you cannot take 5 x's out of here since you only have 2. It doesn't make any sense, right? Do the same thing with your y's. Take a look at each of those powers. Recognize here that the smallest power is 3, so x to the 2nd, y to the 3rd so far. Now let's notice they each have z. By the way, if they didn't all have a z, you can't factor it out, right? It's like, duh, they all have to have it in order to be able to contribute. Looking at your z's, we recognize that the most we can take is z to the 1st. So x squared, y to the 3rd, z to the 1st is actually your GCF. Okay, so I have some tips here for you that I want you to really think about. You may want to even write this on index cards, who knows. Whatever you do for studying, include this for sure. Tips for finding the greatest common factor. For the numeric part of a term, the GCF for the numeric part of a term is found by identifying the largest factor that divides evenly into all terms. Again, what's helpful in this endeavor is making factor pairs. Okay, we're making those pairs. And then for the variable part of a term, the GCF for the variable part of a term is found by identifying the lowest power of the variable found in all terms. Okay, keep in mind that in order to take that out, in order to factor it out, every single term has to have that same variable. So every term must have that same variable. Okay. As we're doing this, I want you all to realize that there are always 2 parts to a term. So when we factor, I'm going to say to you, okay, let's look at both parts of a term, the numeric part and the variable part. As we factor every single time, numeric part, variable part. I want that to be ingrained in your minds. Numeric part, variable part. Okay? Let's check out some examples. Turn the page. Factoring is essentially the reverse process of multiplication. It is like division, except you do not eliminate the divisor. You rewrite the expression as the product of the GCF and its other factor. So every time you factor, think numeric part and variable part of each term. So let me show you what I mean by this. Our first example is 33n plus 12. Again, what may help is go ahead and let's write out the factor pairs for 33 and for 12. So we have 1 times 33, 3 times 11. And that's as far as we go with 33. With 12, we have 1 times 12, 2 times 6, 3 times 4. Looking at both of these sets of factor pairs, notice that our GCF happens to be 3. So for the numeric part of each term, I notice that my GCF is 3. But now let's look at the variable part. Our first term is 33n. It has an n as a variable base, right? As part of its variable term. Let's try that again. This term has n as its variable part. Okay, good. Got it. I can't speak today. Notice that 12 does not have a variable. This is a constant. So when we look at both parts of a term, we recognize that we cannot factor a variable part because the 12 doesn't have a variable. So the only thing we're going to actually factor out is that 3. So here's what it looks like. You're going to take the 3, you're going to divide it out of each term. I'm going to write this out. Divide the GCF from each term. So 3 into 33n, or 33n divided by 3, is 11n. And then 3 into 12, or 12 divided by 3, is a positive 4. And that is how you write your factored form. Notice that we can easily check our answer. If we distributed the 3 and we get the original polynomial, chances are we've done this correctly. 3 times 11n is 33n. 3 times 4 is positive 12. Perfect. That's what we are looking for. I'm going to make a note here. You can always check by distributing to see if you get the original polynomial. Okay? You can always check by distributing to see if you get the original polynomial. Let's try number 2. Number 2 reads 24x plus 38y. Numeric part, variable part. For our 24 and 38, again, we can quickly write these out. 24, 38. So we have 1 times 24, 2 times 12, 3 times 8, 4 times 6. For 38, 1 times 38, 2 times 19, and I'm pretty sure that's it. Yeah, that looks good. Look at both of these sets. Notice the greatest common factor is 2. So we're going to factor 2 out, which means we divide this out of both terms. 24x divided by 2, 12x. 38y divided by 2, 19y. I want you to notice that I was unable to factor out a variable part because they both do not have x and they both do not have y. Think back to the M&M problem where they each had to have M&Ms in order for us to take equal contributions, right? If one had M&Ms and another one had Sour Patch Kids, well, you could say candy, but if you're talking about M&Ms and you want equal contributions, well, you can't take any from the person with Sour Patch Kids because those are not M&Ms, right? I know it's silly to think that way, but I'm actually expecting that this will make a lot of sense using that kind of analogy. Check out number 3. 49m to the 5th minus 21m to the 4th plus 35m to the 2nd power. So again, we have 2 parts to every term. Let's start with the numeric part. We have 49, 21, 35. 49, 21, 35. 1 times 49. 7 times 7 is 49. For 21, 1 times 21, 3 times 7. And then for 35, 1 times 35, and 5 times 7. Right away, I hope you all see that they have a common factor of 7. So that's the numerical part, right? So as part of our GCF, we know that 7 is the numeric part of that. But then we still have to look at the variable part. M to the 5th, M to the 4th, M to the 2nd. At most, we can only take M to the 2nd from every term. Remember, if you wanted to take 5 m's, this one can't give you 5 and neither can this one. If you wanted to take 4 m's, sure, the first term could give you 4 m's, the second term could give you 4 m's, but the third one cannot because it simply does not have it. So look for the smallest power. My GCF then becomes 7m squared. And remember, we're dividing 7m squared from each of these terms. As a reminder to you all, let's think back to the quotient rule. If I had m to the 5th over m to the 2nd power, recall that we would keep the base but subtract the powers and leave it where it's heaviest. So this would be m to the 3rd because we subtract the powers. Similarly, if I had m to the 4th over m to the 1st, notice here, we keep the base, subtract the powers, so it becomes m to the 3rd again. Keep those exponent rules in mind as we move through these problems. Okay. 7m squared goes into 49m to the 5th, or think about it this way, 49m to the 5th divided by 7m squared is 7m to the 3rd power. Negative 21m to the 4th divided by 7m squared is going to be negative 3m to the 2nd power. And then positive 35m squared divided by 7m squared is going to be positive 5. Let's double check. Recall the product rule. The product rule states that if you have bases that are the same and you're multiplying them, you keep the base, add the powers. Product rule, quotient rule. Excellent. So 7m squared times 7m to the 3rd is 49m to the 5th. Keep the base, add the powers. 7m to the 2nd power times negative 3m to the 2nd power is negative 21m to the 4th power. Keep the base, add the powers. 7m squared times a positive 5 is a positive 35m squared. Check. We were able to show that we have the original polynomial by distributing. Good. Now, number 4 is actually a little bit different. I want you to notice what I've written in this box here. If your leading term is negative, you must factor it out. When you think leading term, think of the term that's in the very front, right? Your very first term, your leading term. It's also the term of the highest degree. So notice here we have negative 14n to the 5th minus 28n to the 3rd plus 7n squared. My leading term is a negative 14n. So actually, right off the bat, I know that whatever I factor out, I'm going to have a negative with it. So I'm going to put the negative out front right now. So I have a 14, I have a 28, I have a 7. I think you all can see right off the bat that my GCF for the numeric part is just a 7. And then look at the variable part, n to the 5th, n to the 3rd, n to the 2nd. So the most n's you can take is 2. So your GCF is negative 7n to the 2nd power. Again, we had to factor out that negative because it was in our leading term. Keep that in your minds. That will never go away. So we're going to take each term and divide by the negative 7n squared to write out its other factor. So negative 14n to the 5th divided by negative 7n to the 2nd power is 2n to the 3rd power, right? 14 divided by 7 is 2. N to the 5th divided by n to the 2nd, keep the base, subtract the powers. Negative 28n to the 3rd divided by negative 7n squared. Again, negative divided by negative is a positive. 28 divided by 7 is 4. N to the 3rd divided by n to the 2nd, keep the base, subtract the powers. N to the 1st power. Lastly, positive 7n squared divided by negative 7n squared. Think about positive divided by negative is a negative. 7 divided by 7 is 1. N squared divided by n squared is 1. So that leaves us with a 1. If you distribute, you will get the exact original polynomial. Negative 14 n to the 5th, check. Negative 28 n to the 3rd, check. Positive 7n squared, check. So we know we got this correctly, okay? Go ahead and try number 5 on your own. Negative y to the 4th plus 3y to the 3rd minus 9y squared. I'm only going to give you 2 minutes starting now. Okay, let's check this out. So first things first, we notice that our leading term is negative. So I definitely have to factor out that negative with whatever the GCF is. Then I'm going to look at my numeric part. I have a 1, a 3, a 9. At most, I can only factor out a 1, so I'm not going to write a 1 here unless you want to. I'm not going to. So then I look at the variable part, y to the 4th, y to the 3rd, y to the 2nd, and I recognize at most I can only take out a y to the 2nd power. Okay? Thank you, Ria, Cindy, and Kayla. Excellent. Let's take a look. So I'm factoring out the negative y squared because I don't have anything higher than a factor of 1 as my numeric part for my GCF. So now let's divide each term by a negative y squared. Negative y to the 4th divided by negative y squared is a positive y to the 2nd power. Positive divided by negative is a negative. 3 divided by 1 is 3. Y to the 3rd divided by y squared is y to the 1st power. Right? You keep the base, subtract the powers. Negative 9y squared divided by negative 1y squared, well, that becomes a positive, right? Because negative divided by negative is positive. 9 divided by 1 is 9. And then y squared divided by y squared is 1. So we do not need to write any y's here because they have been factored out. Let's double check. Negative y to the 4th power. Positive 3y to the 3rd power. Negative 9y squared, and it checks. Beautiful work, everyone. Very, very nice. Let's keep going with this idea. Now, what happens when you have terms that look like this? Notice number 1 says 2x times 5x minus 3 plus 9 times 5x minus 3. I said it weird like that because I wanted you all to hear that both of those terms have a common factor. The common factor just happens to be an expression. Notice what I've written here. So, for our first term, 2x times 5x minus 3, this 5x minus 3 reappears in my second term. So, we still want to go through the whole process. First off, notice my leading term is positive, so I do not have to factor out a negative. That's the first piece. Next, I need to think numeric part. So I have a 2 here and I have a 9 here. Out of the 2 and the 9, I can only factor out a 1. They do not have any other common factors, so I won't worry about that. And then variable part. If we look at the variable part of each term, we notice that they both have in common the 5x minus 3. So my GCF, believe it or not, is going to be that 5x minus 3. Now, if I divide the 5x minus 3 out of my first term, do you agree that, and I'm going to write this on the side because I want you to see this. Do you agree that if I take my 2x times 5x minus 3 and I divide by 5x minus 3, that those cancel, leaving me with just a 2x? Very nice. Similarly, with our second term, when I divide by the 5x minus 3, they cancel and it leaves me with a positive 9. And guess what? That is the complete answer. 5x minus 3 times 2x plus 9. All right? It's a little bit of a different approach because you haven't seen expressions being canceled yet. But recognize that that's actually what ends up happening. You're allowed to cancel. They act the same way variable bases would. Let's do that again. Number 2, we have 5y times 2m minus 7 minus 3 times 2m minus 7. Okay. My leading term is not negative, so I do not have to worry about factoring out a negative. Next, I'm going to look at my numeric part. I have a 5 and a 3. These two do not have any common factors other than 1, so I'm not going to worry about the numeric part. Now let's focus on the variable part. If we look strictly at the variable part, notice this one has a y, this one doesn't, but this one has a 2m minus 7, and so does this one. So my GCF in this case is 2m minus 7, and if you factor the 2m minus 7 out of both terms, you're left with 5y minus 3. I want you to visualize crossing off those factors that you've already divided out, right? So by bringing the 2m minus 7 in front, you're factoring it out, which means you're dividing it out of each term. So here is your final answer. Try number 3 on your own. 1 minute starting now. Don't overthink it. Go for it. Okay, so first things first, I don't have a leading negative, so I don't have to worry about that. Notice here I have for my numeric part, I have a 10 and I have a 1 here. So even though it's not written, we can write down that there's a 1 in front of the set of parentheses. More specifically, there's a -1 in front of that set of parentheses. But again, I can't factor out any value for the numeric part. Next, I'm going to look at the variable part. This term has an x. This one does not, meaning in front of the set of parentheses, but they both do have the 9x plus 2. So I'm going to factor out the 9x plus 2. When I do so, Kayla, you're exactly right. You're going to be left with 10x minus 1 in our second set of parentheses. Now, before I move forward, I want you all to recognize that the order of the parentheses doesn't matter because multiplication is commutative. So if you had written 10x minus 1 then times 9x plus 2, they are the exact same expression. Recall that a times b is the same as b times a, right? That is the commutative property. So I want you all to be very comfortable and confident in that. There are going to be cases where our parentheses will not match up. They're going to be in reverse order, and that's okay. That is not a big deal whatsoever. All right, I want you to look at number 4. Let's see if you can get this one correct. I bet anything that I'm going to trick quite a few of you. Good luck. 3n times 4p plus 5 minus 6 times 5 plus 4p. Let's see what you got. So I think the first thing you all noticed was that the 4p plus 5 was the same. Even though it was written 5 plus 4p, that order it's commutative, right? So addition is commutative. So this is the same as 4p plus 5. So the first thing you all did was you said, okay, we're going to take out the 4p plus 5, and then I'm left with 3n minus 6. But what Doc actually did and what Ryan did was they looked a little bit further. They said, well, 4p plus 5, this looks good, right? But then they looked at 3n minus 6 and said, whoa, I have a common factor. I can divide out a 3 from both of these terms. So if I divide a 3 out of both of those terms, 3n divided by 3 is n, -6 divided by 3 is -2, and then I still have the 4p plus 5, so let's write that at the end, and that is our final answer. Nice job. Excellent, Doc. That was perfect. Your order is a little different from mine, but they are the same. Remember, multiplication is commutative. So that's the one thing I tricked you all with, and that was you need to factor completely. Notice one of the things we could have done initially is we could have said, well, my leading terms are not negative, so I don't have to worry about that. But then you could say, oh, wait, the numeric part, I have a 3 and a 6, so I could definitely factor out a 3. Let me show you what something like that would look like. Hopefully that won't freak you out too much. You can always just factor it out afterwards, but really it's going to be a good thing if you get into the habit of factoring it out initially. So let me rewrite the problem. 3n times 4p plus 5 minus 6 times, and you know what? 5 plus 4p is the same as 4p plus 5, so I'm just going to rewrite that. So if we follow the steps from our previous page, we would say leading negative, nope. We would say numeric part, yep. So we have a 3 and we have a 6, so we're going to factor out a 3. And if I factor out a 3 from both terms, that leaves me with n times 4p plus 5 minus 2 times 4p plus 5, right? So you factored out the 3 from both terms. This is one term, this is two terms. So here's a 3, here's one term, here's your second term. And then you say, oh, well, they both have the 4p plus 5, so we're going to take that out. That leaves me with n minus 2, and then there's a 3 in front, so I'm just going to bring that right down. So this is just another perspective of factoring in the same way. It is okay if you factored out the 3 after you wrote the expression out, right? After you wrote the factored form, that's okay. But notice the directions for this page are to factor completely, not factor partially. You're never going to be allowed to factor just part of the way. That's crazy. It's like saying, oh, I'm just going to go 50% here. No, you need to go 100%. All right, last problem. Let's tie all of these pieces together. Check out number 5. Negative 8y to the second power times 11x minus 4 plus 2y times 11x minus 4. This is your last problem. Make it the best. Let's see what you got, starting now. Okay, let's take a look. So we could do this in two ways. We could go ahead and write out our factored form the way we did initially for problem number 4 and then factor out the GCF. Or we could look at it how we did here, which was we factored out the GCF first, like our numeric part, and then our variable part, and we kind of progressed through the problem that way. Here's what I'll do. I'll show you both. So first things first, you're all going to notice that the 11x minus 4 is the term that's in, or the factor that they have in common. So you're probably going to end up saying, okay, well, if I factor out the 11x minus 4, I'm left with negative 8y squared plus 2y. And then you're going to look at each factor and you're going to say, well, this one's done. This is factored completely, but this one is not. And this one's not factored completely because I have a leading negative. I have a common factor of 2. And I have a common factor of y. So out of this side, I'm going to factor out a negative 2y. If I factor a negative 2y out of each of these terms, I'm going to have a positive 4y. That's my first term. And then I'm going to have a negative 1. And of course, I'm going to bring down the 11x minus 4, and that would be my final solution. So negative 2y times 4y minus 1 times 11x minus 4. If you have the order switched, meaning you have negative 2y times 11x minus 4 times 4y minus 1, again, that's the same thing. So we all have the exact same answer, and I love it. If you wanted to look at it piecemeal by saying, okay, let's focus on leading negative, then numeric part, then variable part, this is how you would do it. So first things first, we do have a leading negative, so I'm going to factor that out. Notice I have an 8 and a 2, so I can factor out a 2. Notice I have a y squared and a y, so I'm going to factor out that y. Okay, so if I took out just the negative 2y from both of those terms, then that leaves me with a positive 4y times 11x minus 4. And then it leaves me with a minus 1 times 11x minus 4. Finally, I can say, well, let's factor what's inside the parentheses further. We can take the 11x minus 4, factor it out of both terms, and you're left with 4y minus 1. Bring down the negative 2y, and you're finished. Okay, a couple different perspectives. I kind of feel like most of you are going to lean to this format, which is totally cool. Okay, it works. Why not? If you wanted to do a piecemeal like this, that will work as well. Okay, if you wanted to say, well, my GCF completely is a negative 2y 11x minus 4, or times 11x minus 4, and then say that leaves you with 4y minus 1, that works as well. So it's completely up to you. So this actually concludes our first step of factoring, which is GCF. As we move forward into, exactly, as we move forward to tomorrow's class, we don't have class Wednesday, and then Thursday's class, every time we factor, I'm going to say, what is step one of factoring? And I'm going to imagine that I hear you all saying GCF, GCF, because that is the first step. There will be certain techniques that we will learn that you will not be able to use unless you factor out the GCF first, okay? So get into that habit. GCF is your first step. Don't forget the leading negative goes with this. That's why the flow chart is going to be so nice. So make sure you have this flow chart handy. Keep it aside as we move through this unit. And if you do that, we're going to be super successful. All right? Have a wonderful rest of your day, and I look forward to seeing you all tomorrow. Today's class was awesome. This was really, really great. I'll see you all tomorrow. Bye.